Hello friends, in this video I'd like to solve the following problem from the Croatian Mathematical Olympiad, 12th grade 2003, problem number 4. We wish to prove that if n is a natural number, if p is a prime, then n choose p minus floor of n over p is divisible by p. So it's a very nice problem from number theory. Here are my hints. First, write that n equals pq plus r for some natural number q, and r is the remainder upon division by p, so it's between 0 and p minus 1. Let n choose p be congruent to x modulo p, and try to solve for x. And finally, crucial observation is that if we have p minus 1 integers which are pairwise non-congruent modulo p, so in other words, p does not divide the difference of any two of them, and none of them is divisible by p, then their product is just 1 times 2, is congruent to 1 times 2 times p minus 1. So we have just p minus 1 different remainders, just arranged in different order. So give this problem a try, and I will see you in just a minute. Okay, so here's my solution. So as I suggested, let n be equal pq plus r, where q is a natural number and r is from 0 less than p minus 1. What now? Well, notice first, maybe we'll first evaluate the floor. Floor of n over p is just q plus r over p, but r over p is less than 1, q is an integer, so this floor is obviously just q. And now let's tackle our binomial coefficient and choose p. Let's expand it. Well, n choose p. Maybe let's also write n choose p, also known as eq plus r choose p. Okay, so it's a product which goes from pq plus r, pq plus r minus 1, and so on. Along the way, we'll encounter pq plus 1, then we'll have pq, then we'll have pq minus 1, and we'll continue right to the end. In the end, we'll have pq plus r minus p plus 2 plus 1. Plus 1. It's the last term. P terms in total. And in the denominator, we have p minus 1, p minus 2, and so on, 2, 1, finally. Now, notice the following, that p appears both in the numerator and in the denominator, so we can cancel them. And we can write it as q times pq plus r, pq plus r minus 1, and so on, pq plus 1, pq minus 1, pq plus r minus p plus 1, over p minus 1, p minus 2, 2, 1. Or maybe p minus 1 factorial for the sake of brevity. It's p minus 1 factorial. All right, and now let's say that this entire number, which is obviously an integer, is congruent to x modulo p. Let's say that. Now, we can deduce the following, that q times, maybe let's write q in this peach color, q times this product pq plus r, pq plus r minus 1, pq plus 1, pq minus 1, pq plus r minus p plus 1, that is congruent to x times p minus 1 factorial, because we know that we can multiply congruences by any number. So I have multiplied by p minus 1 factorial, modulo p, of course. Now, the crucial part. Notice that here we have, what exactly? Here we have p minus 1 numbers, pairwise non-congruent. So maybe I need some space, so maybe I will put it a little bit lower. So here we have p minus 1 pairwise non-congruent numbers, integers, none of which is divisible by p. None of them is divisible by p. Well, so the second one is very obvious, but the first one, are they really non-congruent pairwise? Yes, they are. You can check it manually. That if some, for example, maybe let's justify this first claim, star, because it follows from the following. If pq plus r, because every number on this list is pq plus r minus I, for example, pq plus r minus j. Yes, let's suppose that they are congruent modulo p. Well, that means that j minus I is congruent to 0 modulo p. But what is ij? Well, I goes from 1 to, not from 1, from 0. It goes from 0, j as well. So I and j, they go from 0 to p minus 1, but they one value is excluded. One value is excluded because we have p minus 1 terms. So which term is excluded? Well, such that r minus I is not divisible by p, r minus j as well. But now notice that the only possibility for this to be true, we are taking some number from this list and subtracting some other number from this list. So this difference, it's pretty easy to see, this difference is strictly between minus p and p. And the only number between minus p and p which is divisible by p is 0. So, in fact, I must be equal j. So no two different numbers can be congruent. If they are congruent, they must be equal. Okay, so that was the justification of this asterisk condition. And now, since we have p minus 1 numbers which are pairwise non-congruent, by my first hint, there are just 1 times 2 times 3 and so on up to p minus 1 arranged in different order. Is congruent to x, p minus 1 factorial, modulo p. And now, since we have numbers which are not divisible by p, here we have p minus 1 factorial here as well. We can safely divide both sides of this congruence by p minus 1 factorial. And now we see that, in fact, q is congruent to x modulo p, i.e., which means that n choose p is congruent to q modulo p. Okay, but our floor equals q. So finally, n choose p is also congruent to floor of n over p. And that closes our proof. It's exactly what we wanted. That's it. A very nice problem from number theory. Yes, that's it. Thank you for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.